Hello, friends. Welcome to Hydraulics and Hydraulic Machines class. In this lecture, we focus on what is the power saved by having the air vessels in case of reciprocating pump. How much power will be saved? And this power savings is against actually the friction. If there are no air vessels, what is the work done or power to overcome this friction loss? If there are air vessels, what is the work done or power spent to overcome the friction loss? So, by keeping air vessels, is there any power savings? Is there any power that is being saved? How much is the percentage? What is that? So, that is what we discuss in this lecture. So now basically, what is the power saved by having air vessels in case of single acting reciprocating pump? So what I will do, the first is what is the work done or power expended against friction against friction without air vessels. I call it as P1. Next, what I will do, what is the work done or power expended against friction with air vessels. Then what I will do, saving of power. Saving of power is nothing but P2 minus P1 by P1 into 100. This will be how much? The same actually saving of power for double acting reciprocating pump. How much? This is the topic actually. So how I go like this? So let us straight away go into the first article. The first article speaks about the work done or power expended against friction without air vessels. This is the first thing. So now basically we know what is the velocity of flow in suction pipe or delivery pipe. I am making it generalized, which I call it as small v for single acting reciprocating pump is equal to, already we have done, small v is equal to A by A omega r sine theta. This already we have done. Therefore, loss of head due to friction, loss of head due to friction is equal to FL V square by 2GD. It is lengthy suction pipe LS, delivery pipe LD, diameter also suction pipe TS, delivery pipe TD. I am making it generalized. So that is FL by 2GD into A by A omega R sine theta whole square. So if I see this basically here, this head loss is proportional to the square of rank angle theta. So the variation of head loss is parabolic. The variation of head loss is parabolic. So if I see what is the work done or power against friction, if I see per stroke, I means suction stroke or delivery stroke is equal to the area of indicator diagram. So therefore, for example, this is not equal to, this is proportional to. Proportional to the area of the indicator. Therefore, it is proportional to the area of parabola. How it looks like. For example, if you see this is the line, so this is how it is. So this is the HF. Similarly, on the other side, if you take it delivery side, it is actually upper side. So if I take it at theta is equal to 0, theta is equal to 90, theta is equal to 180. So this is at theta is equal to 90, the maximum value. So this area of the thing. So if I take it, what is the, for example, if I take it the area of the parabola 2 by 3, and this is nothing but the length of the stroke. 2 by 3 L into what is this actually, whatever is the that I call it as A by A omega R sine theta whole square into one more thing I forgot, FL by 2GD. Okay, so this all is the friction loss. So this is equal to this HF all. This is nothing but HF into L. Right. So if I take the maximum value, maximum value of HF is at theta is equal to 90 degrees. And if I take that, it is 2 by 3 L FL by 2GD into A by A omega R whole square. And therefore, work done or power is equal to, of course, always it is per second only, is equal to basically what we can write power is equal to, it is gamma A, already L has here, gamma A n by 60 into, what is the remaining thing, 2 by 3 L FL by 2 GD into A by A omega R whole square. So this is the equation, final equation. So what is this? Gamma A n by 60 into 2 by 3 L FL by 2 GD A by A omega R square. This is per stroke. It is for suction stroke, and the same is again for delivery stroke. Per stroke, this is the thing. Please remember, this is per stroke. So this completes to me this. Let me go into the second one. What is the second one actually? Work done or power expended against friction with air vessels. This is the next. So now that what has happened actually, air vessels are fitted on suction, pipe, delivery pipe, very close to suction wall, delivery. This is the position. Because of this, what has happened actually, the velocity in suction pipe or delivery pipe is equal to the average velocity. Is equal to average velocity, and it is constant. There are no fluctuations. If that is the case, what is the mean velocity? Mean velocity of flow, it is V bar is equal to Q by area of pipe. So Q is nothing but actually it is ALN by 60 by area of the pipe small a. Suction or delivery, whatever it is. Now we know omega is equal to 2 pi n by 60. Therefore, n is equal to 60 into omega by 2 pi. This is thing. Further, L is equal to 2R. So substituting, it is equal to A by A. L is equal to 2R into n is equal to 60 omega by 2 pi divided by 60. So 60, 60 if I cancel, 2 I cancel. It is equal to A by A R omega by pi. R omega by, so this is the mean. So mean velocity is equal to A by A R omega by pi. So this is the first thing with air vessels, because when air vessels are fitted, the velocity is constant. So therefore that is equal to mean velocity, because the whole purpose of keeping the air vessels is to maintain actually the velocity as constant. Thereby actually we base the fluctuations in the what you call it as velocity are zero. Therefore, the acceleration pressure head is minimized and is limited to only a small portion, and thereby the friction loss also is reduced. That's what we are discussing, how much is reduced. So therefore, loss of head due to friction, loss of head due to friction is equal to FL by 2 GD into A by A or omega by pi whole square. So this is the thing actually. So now basically the loss of head is of independent of theta, and hence the indicator diagram is a rectangle. How it looks like, if you take it, this is the length of the stroke L. So whatever is the basically the crank angle, whether it is theta is equal to 0, theta is equal to 90, theta is equal to 180, this remains constant. This is the HF. So if you now basically the work done by the pump per second, basically per stroke against friction is proportional to the area of indicator diagram, that is proportional to area of rectangle. So that's why when it is proportional to like that, now it is proportional to L into HF is, what is the HF we got actually? FL by 2 GD into A by A omega R by pi whole square. So this is the thing actually. And now it is therefore the work done per second or power per stroke against friction is equal to basically it is gamma a n by 60, right, into, this is the k value, constant of proportion, L into FL by 2 GD A by A omega R by pi whole square. So this is the equation. There are now two equations, previously one, now these two. Now if I want actually P2, this I call it as P2, whereas previous one is P1. So what is P2? Work done per second or power per stroke against friction with air vessels divided by work done per second or power per stroke against friction without air vessels. So if I take that, so now let us write the equations actually. So this is the first one is gamma A n by 60 into basically 1 into L. This is over. Next, then is F L by 2 GD A by A omega R by pi whole square. This is first one divided by gamma A n by 60 into L, that is there, into 2 by 3, okay, FL by 2 GD, right, A by A omega R whole square. This is the thing. Now if you cancel, all this will go. FL by 2 GD will go. A by A will go. Omega R, all that go. So what is the remaining thing if I see in this is equal to 3 by 2 into 1 by pi square. So that is what I observed. So therefore P2 by P1 is equal to 3 by 2 pi square. So this is what I will get. So therefore percentage of power saved or work saved, anything, is equal to P2 minus P1 by P1 into 100. It is nothing but 1 minus basically, sorry, P, P1 minus P2. P1 is higher. So it is P2 by P1 into 100. So that is equal to 1 minus 3 by 2 pi square into 100, which is equal to 84.8%. Same if we repeat, actually the same can be repeated for double acting reciprocating pump also. The only salient points in that is the work done or power expended against friction without air vessels is same as single acting reciprocating pump. That is P1 is equal to gamma AN by 60 L 2 by 3 FL by 2 GD into A by A omega R whole square. Whereas work done or power expended against friction with air vessels is different because the mean velocity changes and hence friction loss changes. So here what will happen? The mean velocity is equal to Q by area of the pipe. So that is equal to 2ALN by 60 divided by small a. So it will be 2 into A by A omega R by pi whole omega R by pi, sorry. So previously it is A by A omega R by pi. Now it is because double acting reciprocating pump, it is 2 into A by A into omega R by. This is the difference, main difference. Once that is over, rest of the things you can calculate. HF is equal to FL into 2 into A by A omega R by pi p square basically. It is whole square by 2GD. This is the thing. 2A by A always, that you should remember. So therefore, power expended is equal to basically gamma AN by 60 into L into this HF. Right. Then in that case, if I do it, you can write it gamma AN by 60 into L, right? Into basically, what is it actually? FL by 2GD into 2A by A omega R by pi whole square. Therefore, this is P2 and previous one is this is P1. So therefore, P2 by P1 is equal to P1 is basically what we do. P1 is equal to what now? That means without air vessels. P1 is without air vessels. Then with air vessels. Without my P2, sorry, with air vessels. P1 is without air vessels. So it is equal to with the air vessels gamma AN by 60 into L FL by 2GD 2A by A omega R by pi whole square. This is the numerator. Whereas the denominator is gamma AN by 60. It is L into 2/3 FL by 2GD into A by A omega R whole square. So now if you do it, actually we will get 6 by pi square. This is the first. So when we get 6 by pi, previously 3 by 2 pi square, then now 6 by pi square. So what is the work or power saved is equal to, already we have done P1 minus P2 by P1 into 100. It is 1 minus P2 by P1 into 100. It is equal to basically 1 minus 6 by pi square into 100. So it is 39.2%. Excellent. Even from one more questions also, the power saved with air vessels single acting reciprocating pump, it is equal to 84.8%. Double acting reciprocating pump 39.2%. So this is excellent. Even I'm telling you, not a big question, but this is very, very important, please. So at the beginning, actually, if you remember of this lecture, if I go back, actually, please once again look back. So this I have put it as first starting point. Let us take it. Here actually one small mistake basically. Normally what will happen is this is basically uh, without air vessels the power spent is more, and with the air vessels the power spent is less. So this ratio whatever we are talking about, it should be such that actually this is this P1 minus P2 by P1. Apart from that, everything is fine. So now in this lecture, we have completed actually. So the power saved against friction by keeping air vessels is uh, the power saved against friction with air vessels is 84.8% power is saved. So in case of single acting reciprocating pump, and 39.2% is the power saved in case of double acting reciprocating pump. So this completes to me this particular topic. Thank you so much for your patience.
Like, share, and subscribe. Hit the bell icon for more updates.